TAP average data rate, packet/s, and average packet drops. In Figure A we observe that there is a deviation in mean packets delivery delay between the four topologies, as the node density increases. Biased random and simple diffusion placements seem to cope better with the increment of the number of nodes, as this increment creates more data paths. The reason in this case, as well, is the number of nodes around the sink, nodes that can directly forward the data to sink. On the other hand, as fewer nodes are around sink, latency increases due to the hotspot that appears near sink. Concerning the percentage of network's remaining energy, Figure B, we notice that TAP exhibits the best performance compared to the other algorithms. The reason is the creation of alternative paths, that employs almost all nodes in the procedure of packets forwarding from source to sink. Comparing the performance of TAP in the four placements we notice that beside grid placement, on the other three placements, TAP algorithm exhibits very good performance and utilizes more than 90% of network resources. This is a strong indication that resource control algorithms can significantly increase the lifetime of a heavy loaded network. TAP mean packets delivery delay and percentage of network's remaining energy. Flooding is generic routing algorithm. When flooding applies, each node forwards every message to every node that is in its radio range. Since it does not implement any traffic control functionality in case of congestion, then the source's data rate remains the same, Figure A. Figure B presents average packet drops when flooding algorithm applies. As it is expected, packets drops increase while time evolves. The reason lies on the functionality of flooding algorithm. That is the fact that fills network with multiple copies of the same packet. Comparing just the placements, we notice that the placements that present the worst performance in the previous cases, when flooding applies, present the best. Grid and random are the placements with the fewer nodes around source. Counting that flooding algorithm forwards every message to every node in its radio range, it is normal that the placements with the fewer paths limit the number of packets in the network and thus the fewer drops appear. Flooding average data rate, packet/s, and average packet drops. Flooding mean packets delivery delay and percentage of network's remaining energy. The same attitude is depicted with mean packets delivery delay, Figure A. Again, placements that create fewer paths are able to forward the data sooner. Finally, we check the percentage of network's remaining energy when the network stalls, Figure B. In this case we also notice that placements with fewer nodes around source, grid and random placements, present better performance compared to the other placements. The reason lies on the operation of flooding algorithm, each node transmits each packets to all of its children. This leads to a bigger amount of transmissions from the nodes that have many children around source. This happened in biased random and simple diffusion placement, and soon these nodes are getting power exhausted. This leads to the creation of a hole around source and network stalls.